Hey there. We're going to look at combining derivative rules. So we're not going to be learning anything new. We're just going to see how we can put the product rule, the quotient rule, the chain rule together with all the basic derivatives we know, such as the power rule, the derivatives of the trig functions, the inverse trig functions, logs, exponentials, all of it put together in four exciting examples. Let's go. So the first one, let's see here. Let's differentiate, and do not simplify. I'm not worried about simplifying in these uh, big functions. So let's say the first function is y equals secant of x squared plus 1 times tan inverse of 2x. And we want to differentiate this function. So on the surface, we can see it's one function times another, so we better use the product rule. So we'll say y prime equals the derivative of the first function, the derivative of the secant function, times the second function, we'll leave that one untouched, plus the first function, the secant function, times the derivative of the second function, arctan of 2x. Okay? And now we're going to focus on the two derivatives we need to do here. So the derivative of a secant function is secant tangent. So we get secant of x squared plus 1 times tan of x squared plus 1. So that's the derivative of the secant part, but then we have to use the chain rule and multiply by the derivative of what's inside. And the derivative of what's inside is 2x. So I'm actually going to put the 2x out front so it doesn't look like I'm taking the tangent of 2x by putting it out here on the end. Okay, so that is the derivative of this secant function. Secant tangent is the derivative of the outer times the derivative of the inner, which is the 2x. And I'll just carry down my tan inverse of 2x plus secant of x squared plus 1. And then we need the derivative of this arctan. The derivative of arctan is 1 over 1 plus the argument squared. In this case, that's 2x. And then we have to multiply that by the derivative of what's inside, the tan inverse of 2x. Well, the derivative of 2x is just 2, so I could put times 2 out to the side, but I'll just go ahead and multiply it and put it on the top of the fraction. And that is the derivative of the tan inverse portion. Now we have no other derivatives to do, so we'll call that example finished. We're not concerned with simplifying. Okay, let's try another one. Same instructions, differentiate, do not simplify. This function is f of x equals the fraction where the numerator is the natural log of x squared minus 1 over x, and the denominator is 3 to the x power. And since we're differentiating, we'll call the derivative f prime of x. And here we have a quotient rule because we're dividing two functions. So I'll take the bottom times the derivative of the top, and I'm thinking ahead about this 1 over x. I want to be able to take the derivative, so I'm going to go ahead and call the x to the negative first. So at the bottom times the derivative of the top minus the top times the derivative of the bottom. And that's all over the bottom squared. So we have our structure. I didn't do too much at once. I just wrote the quotient rule. Now we need to dig into the two derivatives that remain. So I'll copy my 3 to the x. And then the derivative of the natural log is 1 over the argument. But then I have to multiply that by the derivative of what's inside, which is just 2 applications of the power rule. So that'll be 2x. Since I'm multiplying, it's going to end up on the top of the fraction, or I could put it out here. Either way is perfectly fine. I'm going to go ahead and put it on the top. X squared, the derivative is 2x, minus the derivative of x to the negative first. So I'll bring my power down front, so that actually changes to a plus. X to the negative second when I subtract 1 from the exponent. So that's the derivative of this natural log. Then I've got minus the natural log of x squared minus x to the negative first times the derivative of 3 to the x. I threw this one in there because everybody forgets the derivative of an exponential when the base is not e. So the derivative of e to the x is just e to the x. But if your base is not e, it still repeats itself, so it's still 3 to the x. You just get an extra factor of the natural log of whatever your base is. So times the natural log of 3. And that's the derivative of 3 to the x. And that's all over 3 to the x squared, which is the same thing as 3 to the 2x. And again, we're not simplifying. We have no more derivatives to do, so we are done. Let's try another one. G of x equals log base 5 of the argument. Let's put a fraction in there for the argument. And we'll do 5 over 3x to the 4th. Okay. So again, a log, if it's not a natural log, is difficult to remember as well. So I want to throw that in there. We're going to differentiate. So we have g prime of x. And this is not a quotient rule because it's not a quotient, it's a log. The derivative of log base 5 is 1 over the argument. So 1 over the fraction. Times 1 over the natural log of the base. So the log base 5 derivative is 1 over times 1 over natural log of 5. But then we have to multiply by the derivative of what's inside. Let's just write that down, the derivative of what's inside. And I'm going to write it differently. I'm going to call it 5/3 x to the negative 4th, because that is much easier to differentiate than using a quotient rule here. So g prime of x. We will clean this up a little bit since we're taking an extra step. 1 divided by a fraction just flips the fraction over. So we get 3x to the 4th over 5. Multiplied by natural log of 5, so I just get 5 times the natural log of 5. And then for the derivative of this part, we just do the power rule, and we get 5/3 times negative 4 is negative 20/3 x to the negative 5 when we subtract 1 from our exponent. And if you wanted to simplify more, you could, but we're going to call that one good. So this was not a product or quotient rule to start with. This was just a chain rule. And our last one, let's look at arc sine of the square root of x squared minus 3x plus 4. And let's do this. We're going to multiply that arc sine by the natural log of 5x plus 4. And sorry, I forgot to name the function. Let's call this h of x. Okay, so for this guy, we've got a product of two functions, so we have to begin with the product rule. So let's take the derivative of the first function times the second function. Well, the derivative of the first function is rather complex. It's an arcsine function whose derivative is 1 over the square root of 1 minus the argument squared. So in this case, the argument is the square root of x squared minus 3x plus 4. We need to square that and put 1 minus all of that under a square root. So that's not the entire derivative of this first function. That's the derivative of the outer layer of this function. We have to apply the chain rule and keep going inside. So now we have to multiply by the derivative of the inside function, which is the square root itself. So we have to multiply this by the derivative of the square root function, which is 1 over 2 of those square roots times the derivative of the inside function. Again, the derivative of that inside function is 2x minus 3. So all of this is the derivative of this first arcsine function. It's the chain rule applied a couple times because we have functions inside functions. Well, the product rule says now the derivative of the first function needs to be multiplied by the second function. So we still have to multiply by the natural log of 5x plus 4. Then the second half of the product rule says we need to add the first function. So we'll just copy the arcsine function. Times the derivative of the second function. And so the derivative of natural log is 1 over the argument, in this case 5x plus 4, but then we have to multiply that by the derivative of the inside, applying the chain rule again, and the derivative of 5x plus 4 is just 5. And so if we wanted to, we could simplify this a bit. I'm not going to worry about that part. We could multiply all of this together, putting 2x minus 3 and the natural log in the numerator times the 1s. We could square the square root and distribute the negative. We could do all sorts of things, but that's not the point of this video. The point is just to show you how to apply multiple derivative rules concurrently and how to think of removing one layer at a time. So rather complex derivative, product rule, lots of chain rules, arcsine and natural log, big time functions that you see in calculus. So I hope that makes perfect sense.